Hey guys, today it's time to start a brand new chapter. Welcome back from your break. I hope that you had a nice, refreshing break and that you're ready to get started, and hope that the holidays were good to you. And so I think that we're probably refreshed and ready to get going, start a brand new semester and really give it 110% and finish out this school year. So congratulations on being halfway through the year. I'm really proud of you guys for everything that you guys have done this year. You have worked super hard, and I want you to keep that up. So today we're going to talk about rigid motion in a plane. Now you should have your notes there with you, and I've got a copy over here on the right hand side of what the notes look like. I'm going to do things a little differently today. You're not going to see me handwrite these notes out, but we've got the book, or I've got the book opened up right here. And you can see all the definitions, and we'll talk about them as we go through the page. Now, I'm going to talk about them. I'll show you where the definitions and things are. And all you have to do then is pause the video, give yourself time to write the definitions down, and then start the video again so that I can talk about the next term or the next example. So get that pause button ready. And hopefully we'll get through this in, I'm hoping, less than 15 minutes, but we'll see how that turns out. So 7.1 is on rigid motion in a plane. Rigid motion is basically any motion where you move to a new location. You take a figure and you move it to a new location, but you preserve everything about it so it doesn't change shape in any way. It doesn't change its size in any way. It is identical to what it started, or the shapes that it started and the measurements that it started with. There's, first of all, three of our terms that are right here. Excuse me: image, pre-image, and transformation. And those are, you're to write those in these three spots on your notes page. It says figures in a plane can be reflected, rotated, or translated to produce new figures. The new figure, and this is very important, this new figure is called the image. So you might want to write right over here, the new figure in a transformation. The new, T-H-E, the new figure in a transformation. Then the next term is pre-image. The term pre-image is the original figure. So before we move it to its new location, we call it a pre-image. So on problems that I'm going to give you in the future, I'm always going to give you the pre-image, and you are going to find the location of the image. So the pre-image is the before shot, the image is the after shot. It's almost like, to me, we should have a pre-image and a post-image. That just makes good sense to me. But that's not the way it's done. You have your pre-image, which is your starting figure, and then you have your image, which is your ending figure. And those are all transformations. A transformation is an operation that maps or moves the pre-image onto the image. So an operation that maps or moves is probably an easier way to look at that, the image onto, the pre-image onto the image is a transformation. So you're going to want to write those three definitions here in this location on your notes sheet. Now, we're going to skip isometry for just a second. We're going to go down here to three basic types of transformations. The three basic types, which should be fairly familiar, is the reflection, which is right here, the rotation, and the translation. The reflection, the rotation, and the translation. And you can see those three right here. Reflection is always over a line. All right, it reflects, so it's kind of a mirror image of itself on the other side of the line of reflection, or the line of symmetry is another word, another term for that. Rotation about a point. All right, so we just take it and rotate it. There's always a center of rotation and some radius that we are rotating about. Usually we'll rotate clockwise, but every once in a while you're going to see one counterclockwise. So there are two kinds of rotations. And translation, of course, another word for that is a slide. So I want you to write those in these three spots here: the reflection, the rotation, and the translation. And let's move on. All right, this is our first example, and it's a fairly easy one. I'm going to slide this up so you can see. Naming transformations. This is in your notes. It just says name and describe the transformation. Well, we're going to name this transformation as a reflection in the y-axis. You want to probably say over the y-axis, but we really say in the y-axis. So that's the correct terminology for that. So you can see where the pre-image starts, right here. Here's A, B, and C. And this new location is A prime, B prime, C prime. It's like it's got a little apostrophe right next to it, and that apostrophe shows that this is the new picture. All right, this is the new picture after the transformation. So this part A, name and describe the transformation. This is a reflection in the y-axis. So I don't know if you can squeeze that in right there on your notes or what, but that's what that is. Now B, name the coordinates of the vertices. That's pretty simple. A is at 4, 1. B is at 3, 5, and C is at 1, 1. So that's an easy one. And letter C is ABC congruent to its image? Well, of course it is. That's why we're calling it a rigid transformation. It does not change shape. So that's that. Now, the next thing is an isometry. Let's move on down to the next thing. An isometry is a transformation that preserves lengths. So a rigid transformation is an isometry. It doesn't change, it just preserves all the lengths that it had before. So let's go back up here and fill that in your notes. An isometry is a transformation that preserves length. So if we go to example 2, example 2 shows you choice A, B, and C. And we have to look at each one of these and decide whether it is an isometry or not. This one does appear to be an isometry because when you reflect this, it looks identical to what it was before. All right, it's reflected over that line and it appears to be exactly the same. So yes, I would put yes, an isometry. On B, not an isometry. No, we cannot change shape. That's not going to happen. So if it changes shape, and you can see here it got smaller, then that totally messes things up. Not an isometry. And then here, of course, this is an isometry because it's just a rotation to a new location. The picture appears the exact same, and so yes, it is an isometry. Pretty much we're going to just everything we deal with just about a reflection, a translation, a rotation, those are all isometries. All right, so that takes us to the next section, 7.2. There's a few more examples there in your book. You can see over there that if you want to go back, you can check those out and read through those. It wouldn't hurt at all. But I'm going to move on into 7.2, reflections. All right, a reflection in a line M, we're going to take each one of these transformations one at a time and talk about them. A reflection in a line M is a transformation that maps every point P in a plane to a point P prime so that the following properties are true. And here are your properties. If P is not on M, then M is the perpendicular bisector of P prime. Let me read that again. If P is not on M, line M, then M is the perpendicular bisector of P to the line segment from P to P prime. So let's say we take P and we reflect it over the line M and we stick it here. And let's just say, for instance, that we connect that with a line segment. That line segment is the perpendicular bisector of P and P prime. This line here line M, becomes the perpendicular bisector of this line segment that we drew between where P was and where P is now. The pre-image and the image. So we always just connect a line. It's just by definition. We don't really draw the line. The line's kind of an imaginary line. They've drawn it here for you just so you can see what it looks like, but it's kind of an imaginary line. That's the definition. That's how they define reflection. Now number 2 says if P is on M, then P is equal to P prime. So in other words, there's no distance. It's not like we can draw this line between them because P is the reflection of itself. P and P prime are the same because it's sitting on the line of reflection. You can't reflect very well over something when you're sitting on it. So that's why they need 2 steps. Make sure you get those written in your notes right here. All right, example 1. Example 1, graph the given reflection. All right, H -2, -2 in the x-axis. Now you see that's a little bit different than the example that's here in the book. All right, so let's go over to -2, -2, which is going to be down here on your notes, and we're going to reflect that over the x-axis. Now, since it's reflecting over the x-axis, and let me make this a little bit bigger. See if I can make that a little bit bigger. Whoa, there we go. So since it's right here and we want to reflect it over the x-axis, we want it to jump this way, okay, over the x-axis. So it's going to start here, and since it's 2 units away from the x-axis, then we're going to want to go 2 units on the other side and put H prime. All right, so it starts out at -2 and it's going to end at -2, 2 if we reflect in the x-axis. M then is at 4, 5, so go ahead and go over 4 and then up 5, kind of put it about right here. We want to reflect that over the line y equals -1. So you're going to have to draw for me right now. Remember, y equals -1 is a horizontal line right here. So why don't you draw that line of reflection in right there. I wish I could draw it with you, but I can't. I'm using a little bit different software than I normally do. So draw that line of reflection, put your point at 4, 5, and make 4, 5 jump over that line. All right, and just land right below it, making sure that the distance that it is from y equals -1 is exactly the same on both sides. All right, check with your neighbor or with a partner or with a friend. Make sure you did that right. All right. Question. If the point xy is reflected over the x-axis, the new point will be. All right, so let's take a point like, let's say right here. 3, 3. Well, actually, we did it on A, so that'll work out perfect. Here was -2, 2, and we reflected that over the x-axis, and it ended up -2, +2. So that the x value was still -2, but the y value changed to +2. So in general, the x stays the same, but the y makes a negative y. All right, it goes negative x, and I'm sorry, the x stays the same. So I want you to make an ordered pair just like this, and the x is going to stay the same, but then you're going to put a negative y in this spot, and that's what goes in this blank, x comma negative y with parentheses around it, because the x stays the same, but the y is opposite. Now, if we reflect it over the y-axis, so let's say we go, let's say our point is at -2, 2 right here, but we reflect it over the y-axis. Well, now the y stays the same, but the x changed to +2. So it would look, the ordered pair would look like negative x comma positive y, because the x flips and the y stays the same. So that's in general. I want you to check that with me to make sure that you understood that and that you wrote that correctly, since I can't write it there for you. We do want to just double check to make sure everybody has the correct answer, but there should be in this blank a negative x comma positive y, and put parentheses around that. All right, example 2.